In this video, we'll look at the idea of conjugate acid-base pairs. So Brønsted said that acids are things that donate protons, and bases are things that accept protons. But of course, if something's donating, something else has to be accepting. And this means that there's always going to be acids and bases in solution at the same time. Let's have a look at our last example where we looked at ammonia. We said ammonia is actually a base, according to Brønsted. And the reason it's a base is that it is able to accept a proton from water. So if we look at the water here, it is capable of giving a proton to the ammonia molecule. And so on the other side of the chemical equilibrium, we've got the ammonium ion, NH4+. Okay, so that is ammonia that has received a proton, and the water lost a proton, so it is the OH- ion, the hydroxide ion. But if we look, this is an equilibrium, which is to say that it can go forwards and backwards. So the ammonia on this side will receive a proton from the water, but on the other side, it's got that extra proton, which it can give up and return to the OH- ion. And so going in the back direction, essentially you've got this reaction going on. And because of that, we can point to the ammonia over here and the ammonium over here. And we can say over here on the left, it is acting as a base because it is accepting a proton, and over here it is acting as an acid because it's donating a proton. And so this forms what we call a conjugate acid-base pair. And you can see they only differ by a proton. And the one that has one more proton is the acid, and the one that has one fewer is the base. And we can also see another conjugate acid-base pair in the case of the water and the hydroxide ion. So over here on the left, the water is donating a proton, so it's behaving like an acid. And on the other side, it is receiving a proton, so it's behaving like a base. And so that means that these two are essentially identical. They only differ by a proton. And so this is the second conjugate acid-base pair. And so we're always going to see these pairs of pairs, I suppose. So let me write up an example of an equilibrium, and maybe you can identify the acids and the bases and what the conjugate acid-base pairs are. Here goes. Okay, we have an equilibrium here, so let's try and identify the acids and the bases. We really just have to see the things on both sides and ask ourselves which one has one more and which one has one less proton. So here's something with phosphorus in, and on this side it's got 2 protons, and this side it has 3. So it must have gained a proton, and we can only gain a proton from the other thing it's reacting with, so that must be the HSO4-. So we can follow the proton here, and again in the other direction we can see that the H3PO4 must be given away the proton to return to the original side. So that allows us to identify the acid-base pairs here. So the H2PO4 is accepting, so it is the base. And on the other side, it is donating, so it is the acid. So this is one of the conjugate pairs. And again, if we look at the HSO4- on the left-hand side, since it is donating, it is the acid. And on the right-hand side, the thing with sulfur in is accepting a proton, so it is the base. And so that is our second conjugate acid-base pairs. And again, it's really exactly the same molecule on each side. It's just on one side it's got one more proton than the other. So this one's got 2, this one's got 3, so this is the acid. This one's got 1, this one's got 0, so this one has one more, it's the acid, and the other one has the base. Did you find them okay?